And so we're going to be, we'll be starting here in just 1 second here. So
So Eric, can you watch the time on your phone? I think
yes,
you're still 2 minutes before 1 o'clock, so please don't start quite yet.
As far as I can tell, I don't think they're going to change like the actual shape of the.
all right. So welcome to session 4. So our first speaker is Ben Bogart from Concordia College Moorhead, and he's going to be talking about the Minnesota Space Grant Consortium Quadcopter Challenge, a TA perspective. Ben, go ahead and take it away.
Awesome, thank you. Can you guys see my slides again?
Yes.
Yes, okay, excellent. So yeah, today I'm just going to talk a little bit about the MN Space Grant Quadcopter Challenge and what I have done as a TA. So I'll just talk about the challenge just generally, and then I'll talk about my role as TA and the 2 different years that we have done this challenge and some of the modifications we've had to make because of COVID. So first of all, just broadly, with the Quadcopter Challenge, this is a year-long competition in which teams are tasked with building a drone capable of navigating and exploring an unknown indoor environment. This is over the course of the school year. So in the past 2 years, teams have started in October, and then the actual fly-off was in March. So it's a fairly long time frame that they have to work on this. This program is designed to enhance student and faculty capabilities in STEM areas of interest. So specifically, these include things like learning how to pilot a drone, learning how to solder electronics, learning how to wire those electronics, learning how to program different microcontrollers and make them interact with different sensors or telemetry devices. And then also just learning how to use things such as CAD, 3D printer, laser cutting to do physical prototyping for the drones as well. Throughout the course of the challenge, we also required that teams create a series of presentations. These were in various different formats. The first was a preliminary design report, which basically was a written report that highlighted what the team had done so far and what they were planning to do with their design to create a quadcopter that could successfully meet the needs of the challenge. They also were required to orally present all the work that they had done before the fly-off, highlighting some of the challenges they faced, but more so their actual design and all the hardware that they were using. And then they also, post-contest, were required to make another video report that highlighted the results of their fly-off, what data they collected, the sorts of things they found in their unknown environment, and all of that good stuff. So this little picture here, this is an example of the unknown environment. You have some sort of a tower here, some sort of an unknown water sample, and lots of other things for the team to explore. So for the contest, the drone had to be capable of doing the following things. It needed to collect a variety of sensor data. This included temperature, pressure, relative humidity, and magnetic field. The drone also had to be able to collect 1 cubic centimeter of both a liquid and a solid sample, as well as take downward-looking and outward-looking photographs. The team needed to modify their drones in any way they saw fit to make it capable of doing these things. We also, to encourage creativity and above and beyond functionality, teams were awarded supplementary points for including things like telemetry, additional sensing capabilities, or making modifications to the body of their drone that would allow them to better navigate the environment or more easily collect their data. So the first year we did this drone, we provided first year we did this contest, we provided teams with a kit that allowed them to build a basic quadcopter. I say basic because it was actually a fairly complex process putting the whole thing together. This kit was based off the DJI F450 quadcopter, but the parts for the electronics and things were compiled from a variety of different sources. So there was no singular set of documentation that allowed you to put the drone together from scratch. So we created this documentation and provided it for the teams that allowed them to put together this kit and have a basic functioning drone. And you can see an unassembled version of what the DJI 450 quadcopter looks like down there on the right. And then also down on the left, you see an Arduino Uno. I'm sure many of you are familiar with that. We also provided teams with an Uno and some basic sensors just to get them started programming with a microcontroller and getting an idea of the sorts of things they would be able to do and would need to do with sensors to be able to collect magnetic field data and that sort of thing. And then once teams had assembled this drone, they were allowed to modify it in almost any way they saw fit. They weren't allowed to do things that, quote unquote, hacked the drone or made it unsafe, but in general, they were allowed pretty free reign. So as TA, what I did in this first year is I created Arduino and sensor tutorials based on the components the teams were provided in their kit. And that was just so they had kind of a one-stop shop to get started. They would have everything they needed and would be able to introduce all team members into this, the programming and electronics front in case some of them didn't have experience with that before. I also, as I mentioned, the kit had parts from many different sources. So I was the one that compiled all the necessary documentation to build the basic drone. This was probably, these two things were about the first third of the year for my role. And they took most of my time during that. And then once I had completed those two things, I moved into more of an advising role. And to do this, I hosted bi-weekly check-ins and Q&A sessions with the teams. And this was before COVID. So we were using Zoom to do this. So we were using Zoom kind of before it was cool. So once we had to switch over, I was kind of the expert in Zoom. And yeah, so during these meetings, I just tried to get a feel of where each team was at, what they were struggling with. And if they had any questions or troubles with anything, that was a time when they could ask me and I could hopefully articulate what it was they were going wrong. So there on the left, you see a picture of me. This is actually with the F450 drone fully assembled. That was me shooting a video just to show them how to fly the drone. Actually, we noticed some of the teams were having maybe a little more problems with that. So we created a video to help them out. So unfortunately, the fly-off was supposed to happen in March, but we had COVID, so that didn't end up happening. Instead, we modified the post-contest video report to focus on the lessons the teams had learned and any advice that they might have for somebody picking up this project in the future, maybe even using the exact hardware and designs that they were using. We sort of frame this around maybe think, oh, your project's been canceled. This is kind of the last thing you're going to do, so then you can pick it up again in the future. So even though we still had COVID going on, we modified the contest for 2020 and 2021 that would allow us to succeed. One of the major modifications we made is we were going to do the fly-off remotely, and that actually happened these past weeks here. Teams did the fly-offs. I'll talk a little more about the results for that later. But the other major modification that we did is we used a smaller pre-assembled drone instead. And you can see that down there on the right. That's the Blue Heron. This was an interesting change because it significantly reduced the contest workload, but it also induced some additional challenges. This drone didn't have nearly the payload that the bigger drone did, so weight became probably the biggest thing that the teams had to think about this year. We also replaced the Arduino Unos in the kit with Teensy 3.5 microcontrollers. And this was both because these were much lighter and more powerful than the Arduino Uno, and in case there were repeat members from the past year, they would get some experience playing with a different microcontroller instead. So right here, you just see a picture of these two different drones as well. So you can kind of see the scale comparison. The one on the left is the kit drone, and the one on the right is the pre-assembled Blue Heron. There's quite a difference in size and payload between these two drones. So as I mentioned, we just the last couple weeks, we're finishing off our fly-offs that were done remotely. And I was very impressed with what the teams were able to do. 9 out of the 11 teams that entered the contest completed all the prerequisites for the fly-off and were able to participate. All 9 of the teams collected photos and videos. All 9 of the teams also collected liquid samples, and 7 out of 9 and 8 out of 9 collected sensor data and solid samples, respectively. Now, I was really impressed by how well the teams were able to collect solid and liquid samples, because this is quite difficult, especially with this smaller payload drone. It requires some very precise maneuvers in order to actually scoop up some sample and bring it back to their base station. So overall, I was very impressed and very pleased with how this all went. So just to summarize all this, the main goal of this challenge is to enhance student and faculty capabilities in STEM areas of interest. That includes everything from programming microcontrollers to flying a drone, to even those more soft skills like the composing a preliminary design report and that sort of thing. And this was done by challenging teams to build a drone capable of navigating and exploring an unknown environment. And I think overall, this contest achieved that. We had good feedback. Teams said they learned a lot, and in general, it was a very positive experience. On my side of things, I think that serving as TA has really allowed me to not only become more proficient in these areas as well, but it also has really developed my abilities to be a leader in a STEM environment. It's something that I very much feel like I need to learn through experience, and I'm very thankful for the opportunity to do this because of that. And then also just another thing, kind of a side note, this challenge, teams or schools could do something like this outside of the challenge. They could put together a team, buy them sensors, buy them a quadcopter, and say, hey, we're going to build an unknown environment for you. It's your job to explore it fully and give them a time frame, give them some preliminary design things. This doesn't necessarily have to be something that takes place in a contest like this. You could certainly do this by yourselves at a school. So just to wrap things up, I'd like to thank both Thelma and James for all the things that they did organizing this contest and bringing me on as TA, as well as Jamie Van Orschel. He worked with me last year as TA as well. So thanks to those people for making that possible. So at this point, I'll open it up to any questions people might have.
Great, thank you, Ben. We've got enough time for probably a couple questions. We got about 2 minutes. So questions from the field? I certainly have a couple, but.
So this is James. My classic question is, why would NASA care? This is kind of rinky-dink stuff, or maybe not.
Yeah, so NASA might care about this because, well, as you might know, the newest rover on Mars actually brought a quadcopter. So this is a very, I would say, applicable challenge to exploration in space, say Mars or that sort of thing. So learning about these things and the sorts of challenges associated with exploring an unknown environment is definitely applicable to NASA. Other questions?
I had a quick one. As a TA, what was the thing that was usually the most asked as you as a TA? What would folks most struggle with and ask you help for?
That's a good question. In the first year, a lot of what people struggled with was stuff that actually had to do with assembly of the drone. There was some very finicky things. I remember one thing that a lot of teams did wrong was when you wired up the motors that went to each propeller, you had to wire them to the brains of the drone in a very specific manner. Otherwise, the drone would just flip over and crash. And this was something that was done differently depending on what brains you were using. And so a lot of teams that maybe weren't reading my instructions close enough or were going to other things came asking me, hey, our drone keeps flipping every time we try to take off. What's going on here? So Yeah, I guess in general, there wasn't maybe one specific thing, but I did notice that
1
when
minute.
things were going wrong, generally there was 2 or 3 teams that didn't understand something, which generally pointed to me not explaining something well enough or just having gaps in the documentation.
Great. Thank you for that response. All right. Thank you, Ben. Let's virtually thank our speaker. And